First, our formula. We have E pot or E potential energy. That we can measure that in how much we weigh, that is mass, in kilograms, and G, which is gravity, acceleration, and height. And in this case, we have a height of 6, but there isn't free fall here, so yeah. But that actually doesn't matter because friction, as you see over here, is at none. So it will be the same as if he was in free falling. Yep. And we have a mass here that determines how big he is and so on. And over here we can see the potential energy and the total of energy and the kinetic energy. And we have thermal energy, but that is always going to be on 0 because we have no friction. Oh, I went into the wrong one. We have no friction, and that means no thermal energy. So see here, when I put friction up, thermal energy comes up. So put that down and there will be no thermal energy. Whoop. First off, we're going to start with the small man. He has a small mass, he is at height 6, no friction, and only gravity acceleration is going to affect him. So we put him down, you can see the potential energy goes down and kinetic energy goes up. And it keeps doing this over and over again. And here we have. You can see it's up round here. So if we took him for a bigger mass, he'll be one third, 2/3 bigger than the small one, and that is how much the energy also raises. So if he has a higher mass or a higher height, that determines how much energy he has. For example, if we go into here, here, we have a smaller height, which means less potential energy. And of course there's more curves around here, but we still have less energy because there's less height but the same weight. If we take the small guy, who's 1/3 of the big guy, he also has less energy than he has on the other one. So that is potential energy and how we can measure it. So you can say that the measurement is the small is 1/3 part the way of the big guy. Yep. Cool. Yeah. Hello. Kinetic energy. That is the moving energy, which is between, or if we have paragraphs. The potential energy is the energy that is potentially in every single movement. And energy can go into a lot of things. For example, kinetic energy and thermal energy. Those are the ones we have here. Thermal energy is not really optional right here because we don't have any friction. Friction makes the energy, for example, if I let this guy just work with me, see then now there's thermal energy because there's friction. But since we have no friction in this game as we play it, we don't have any energy loss there. So if I have this guy and wants him to go 2 meters, from 2 meters, that's here, about minus, massa minus, you know, then he has that much potential energy, and it all will go to kinetic energy, which is moving energy. So if I let this guy slide, he'll go to a certain speed, and I want to figure out how much. So he's coming down. You can see the kinetic energy is going up. He's coming down, and it went right here. So 1, 2, 3, 4, 5, 6 lines. So of course I have a question for myself. Can I get him to have the double speed? Sure, I just need to go high, right? Because, well, it's the only thing that gives me energy, and that is height. So if I want to double my speed, I just need to get to the double height, right? So potential energy up here, we take it to 4 meters and let him drop. See how much it comes. It needs to go all the way over here. And yeah, he continues. It was about there. Alright, that wasn't enough. Wow, such a surprise. Let's take to 8 meters then. So 4 times the height. Maybe that will give us the speed we want. Let's see. It's about it. You see all the potential energy is coming down. It's going down. And he makes it. He even makes it a little bit more. But yeah, as you can see that he doubles his speed because he has 4 times the original height to double the speed. And if we take our example from our formulas, you can see here we have the potential energy formula, which is height times mass times gravity acceleration, and kinetic energy 1/2 times the mass and times the velocity in second, I think it is in English. So if I have a guy who has a weight at 60 kilos and is 2 meters tall, you see this over here, he will have 1178.4 joules in potential energy. Since we don't have any thermal energy and assume there's no other energies in play when the app then the amount of energy must be the same in kinetic energy, which would be the same number as up here. Now we can see, then we can just solve it and say half times 60, because that's our weight, times velocity in 2 equals this. And I want my program here to find my velocity. I have set over here, so I don't get 2 answers out of it, that the speed is over 0. And it has a number over here. It says 6.2 meters a second. Alright, that's good. So if I want double speed of my guy going down the ramp, the ramp was 2 meters tall, he was 60 kilos, and so on. How much speed do I need? Or if I want double the speed, that would be about 12 in second. How much energy would that produce? Or would it have? It would have 4,713.61. Again, I just use solve, but now I use it up here for the potential energy formula, and it says I have 60 kilos. I know what gravity acceleration is times height, because I don't know that, and how much energy I want, and I want height. Then it says, oh, you need to go to 4 times the height, and here it is. That's your proof for I need to go to quadruple height. Yeah, there's also another thing about this speed speed here. If I let this guy down and he will travel down, he will have a certain speed. It will all be about how much kinetic energy and how much potential energy there will be. Except at the last bit. If I just put it on slow motion. This guy up here. Here he will have a certain amount of potential energy and kinetic energy. Or total energy. They will all convert to kinetic energy. But watch the speed. The speed will continue to rise until there's no more potential energy. See, it's almost down now. And it's almost at the highest peak. So we would say, since there's no friction and our mass isn't gonna change and all that, yet still, if you saw that, the speed just jumped back. That is because this program is actually pretty advanced. It knows when I drop things hard down that a thermal energy will appear. And some of that thermal energy comes from the kinetic energy. Like, for example, if you slide your hand against the table, your hand and the table become hot. And that's because the kinetic energy creates friction. But since we didn't turn any friction on, yet it still recognizes that, well, two items hitting each other will turn some heat around. So, for example, if I drop him here, he would create a lot of thermal energy because he fell from this all the way down and created thermal energy. For example, if I had it